last 7-minute summary for the modern physics, particle physics and cosmology. A very interesting chapter, quite a lot of sections, 12 sections. So I don't know, should I do a 7-minute summary? Maybe I should. Okay, I will do a 7-minute summary. Let's just read the sections for the fundamental forces in nature, positrons and other particles, mesons and the beginning of the particle physics, classifications of particles, conservation law, strange particles and strangeness, finding patterns in the particles, quarks, multicolored quarks, the standard model, the cosmic connection, problems and perspectives. Should we do a 7-minute timer? You know what? Let's not do a 7-minute timer. We're just going to go through this kind of smoothly, kind of slowly. It's not going to be a 20-minute long video. I'm still going to keep it around like 7 minutes, but I got a timer up here seeing how long the recording is. So we're just going to check it out like this. The word atom comes from the Greek atomos, which means indivisible. All right, that's enough for that first paragraph. The fundamental forces in nature. Cool. Field particles, exchange particles, gauge bosons. Okay. All right, this is interesting right here, this table right here. Particle interactions. Interaction, we got 4 fundamental interactions. So we got gravitation, the weak force, the nuclear force. Sometimes this is called the weak and the strong nuclear force, and electromagnetism. Relative strength, you can see nuclear is 1. Gravity is super weak here because its relative strength is times 10 to the negative 39 of the nuclear force. And then electromagnetic and weak are kind of here, like negative to the negative 2 and to the negative 5 here. Range of force. Electromagnetism range of force is infinite. Gravitational range of force is infinite. Weak and nuclear are fairly short. They act on the order of femtometers, which are really small, like times 10 to the negative 12 meters or something like that. Mediating field particle, gluon, photon, bosons, graviton, very interesting. Mass of the field particle. The only one that has a mass is this guy, the field particle. Okay, I don't know what that means. Ooh, Paul Dirac. This dude, bro, this guy actually killed it. This guy theorized the positron. Dirac was instrumental in understanding the antimatter and unification of quantum mechanics and relativity. He made many contributions to the development of quantum physics and cosmology. In 1933, Dirac won a Nobel Prize in Physics. W. Dirac. Positrons and other antiparticles. This is the second section. Interesting kind of graph here. We're going to name Carl Anderson. We're just going to zoom through here. Oh, check this out. Bubble chamber. So the gas chamber here that showed how like particles and stuff move. You shoot it through here and it bends down. It might have a specific charge. It bends up. It might have a different charge. You can see here, the ones that bend down are blue electrons. The ones that bend up are E with a plus, positron perhaps. We got pair production. Cool. Electron plus positron equals 2 gamma. What is gamma? Do they say it anywhere here? They don't. We're going to go back and read through it. We got a PET scan. Interesting. Mesons and the beginning of particle physics. All right. Ooh, we got Yukawa. I've heard of this guy, the Yukawa potential. I've seen that in a quantum physics course, but we're not going to read through this too much. Mesons and the beginning of particle physics. So 1907 to 1981, this is the beginning of particle physics. Like we've already discovered quantum mechanics. We've started figuring this out. And then people, really smart people, start piecing stuff together. Mr. Richard Feynman, kind of in the 1940s, 50s, 60s, 70s, they start piecing stuff together, little graphs like this, little equations and stuff, and they start kind of unifying all particle physics. Classifications of particles. So let's take a look at this. We got a bunch of different particles: leptons, hadrons, mesons, baryons. You can see a bunch of them here. Baryons, under the baryon category, we got the classics: proton, neutron. Where's the electron at? Leptons. Electron is a lepton. Okay, is there a photon over here? I swear there's a photon. Photon is gamma. I know this, but they don't got it right here. Maybe muon, neutrino, tau neutrino, pion, kaon, eta, proton, lambda. Bro, where's the photon at? Maybe the photon is not here. It's not a particle. Should be though. Interesting. So take a look at this picture. This is also something that can get a conversation started. Just have this printed out, and on the train you can show it to someone and get a conversation going. You can make a cool friend like this. Show them these little symbols here. Also, these are good names for children. Neutron, Jimmy Neutron right here. Lambda. Name a kid Lambda. He's gonna succeed. Sigma. All right, we're gonna move on from the baby names. Hadrons, mesons. Here they explain, I guess, all of these things, right? Remember we read hadrons, leptons, baryons, all that. So here they have a small description of each. We got leptons, what they mean. Fermilab, in July 2000, each 6 leptons has an antiparticle. Conservation laws. Okay. Baryon number, I guess, is conservation of baryon number. Whenever a nuclear reaction or decay occurs, the sum of baryon numbers before the process must equal the sum of baryon numbers after the process. Cool. Checking baryon numbers. First kind of example here. Detecting proton decay. Look at this. What is this picture here? Is this a scuba diver? And he's surrounded here with a bunch of plates. Interesting. 17 million years in blue, and they put an exclamation point. The decay constant represents the probability of one proton decays in 1 year. The probability that any proton in our glass of water decays in 1 year interval is given by equation 1, which is this, I guess. Therefore, we must watch our glass of water for 17 million years. That indeed is a long interval. Okay, I'm just curious why they wrote 17 million years here. They wrote 1 month here for different problems. Try those problems out. Lepton number, this is another conservation principle. Whenever a nuclear reaction or decay occurs, the sum of electron-lepton numbers before the process must equal the sum of electron-lepton numbers after the process. Conservation. Checking lepton numbers, another interesting example. Strange particles and strangeness. Many particles discovered in 1950s were produced by the interaction of pions with protons and neutrons in the atmosphere. A group of these, the kaon, lambda, and sigma particles, exhibited unusual properties both as they were created and as they were decaying. Hence, they were called strange particles. Okay, interesting. We got some graphs here. This bubble chamber photograph shows events, and the inset is a drawing of identical tracks. Really cool. So this drawing, I guess, was a theory. Strange particles are formed at the bottom as pi particles act. Okay, I'm not going to read all that. My head is hurting a little from looking at all these graphs and numbers. Conservation of strangeness. Another conservation law. Let's push through that conservation section. Finding patterns in particles. Okay. We got Murray-Gell-Mann. 1969, Murray-Gell-Mann was awarded the Nobel Prize in Physics for his theoretical studies in dealing with subatomic particles. Interesting. I don't know this gentleman too well. But I guess he's important to this section here. We got some more graphs right here. A lot of like experimental analysis in the particle physics era use these kind of bubble chambers. We got quarks. Maybe you've heard of quarks before. You could see here quark composition of 2 mesons and 2 baryons. So if you break down a neutron and proton, you can see they're made of several different quarks. The original quark model, 1963, Gell-Mann and George Zweig independently proposed a model for substructure of hadrons. According to their model, all hadrons are composed of 2 or 3 elementary constituents called quarks. Really interesting theory, man. It's like you can keep breaking the world down into smaller and smaller Lego pieces. There you got properties of quarks. All right. We're just going to zoom through. I don't want to read that too much. Charm and other developments. Although the original quark model was highly successful in classifying particles into families, one discrepancy occurred between its predictions and certain experimental decay rates. Consequently, several physicists proposed a 4th quark flavor. In 1967, they argued that if 4 types of leptons existed, as was thought at the time, there should also be 4 flavors of quarks because of an underlying symmetry in nature. The 4th quark, designated C, was assigned a property called charm. A charmed quark has a charge of, okay, this is crazy, man. There's so much stuff going on here. We got quarks, they're strange, they're charm. Like, what is this? Quark composition of several baryons. We're going to zoom through. Crazy chapter, as you can see, and this is really modern physics, like 1960s. There's definitely people alive that you can ask about this stuff, and this stuff was developed as they were growing up. Multicolored quarks, more stuff about quarks here. I'm just going to zoom through them. Quantum chromodynamics, very crazy. A green quark is attracted to anti-green quark. What, man, they really name stuff with crazy names here. Let's look at the same interaction for a viewpoint of quark model shown in figure 46.13. Okay, I'm not going to look through that either. The standard model, this is the culmination of all of this. Scientists now believe there are three classifications of truly elementary particles: leptons, quarks, and field particles. These three types of particles are further classified as either fermions or bosons. Quarks and leptons have spin 1/2 and hence fermions, whereas field particles have integral spin of 1 or higher and are bosons. Recall from section 46, the weak force is believed to be mediated by the W plus, W minus, and Z0 bosons. These particles are said to have weak charge, just as quarks have color charge. Okay. In 1979, Sheldon Glasgow, Glashow, Abdus Salam, and Stephen Weinberg won the Nobel Prize in Physics for developing a theory that unifies the electromagnetic and weak interactions. This electroweak theory postulates that the weak and electromagnetic interactions have the same strength when the particles involved have very high energies. Okay, let's move through. Matter and energy. Forces, gauge bosons, fundamental particles. Okay, so I guess they're trying to explain these fundamental forces with their particle theory. We've got gauge bosons. Here's the photon. Let's go. The photon is a boson. There's definitely a rap somewhere written in here. Fundamental particles, we got quarks and leptons, and then we got all the forces here, and all of this is matter and energy, the standard model of particle physics. So this is really a conversation starter. If you have this screenshotted, you could show it to people. The standard model, you could talk about this for hours. But right now I kind of just want to finish the 7-minute summary. We're zooming in. A shower of particle tracks from a head-on collision of gold nuclei, each moving with energy 100 gigaelectron volts. This collision occurred at the relativistic Heavy Ion Collider, RHIC, at Brookhaven National Laboratory, and was recorded with the STAR solenoid tracker at RHIC detector. The tracks represent many fundamental particles arising from the energy of the collision. Super interesting. Look at this. This looks kind of like an eye. The cosmic connection. In this section, we describe one of the most fascinating theories in all of science. Let's go. The Big Bang theory of the creation of the universe and the experimental evidence that supports it. This theory of cosmology states that the universe had a beginning, and furthermore that the beginning was so cataclysmic that it is impossible to look back beyond it. According to this theory, the universe erupted from an infinitely dense singularity about 14 billion years ago. The first few moments after the Big Bang saw such an extremely high energy that it is believed that all four interactions of physics were unified and all matter was contained in a quark-gluon plasma. The evolution of the four fundamental forces from the Big Bang to the present is shown in figure 46.16, page 1470, which is the next page. We're going to check on that right now. Boom, here we go. Time in seconds. Interesting. During the first 10 to the minus 43 seconds, the ultra-hot epoch, T equals 10 to the 32 Kelvin, it is presumed the strong electroweak and gravitational forces were joined to form a completely unified force. In the first 10 to the negative 35 seconds, so a little amount of time after this ultra-hot epoch, following the Big Bang, the hot epoch, temperature equals 10 to the 29, symmetry breaking occurred for gravity, while the strong and electroweak forces remained unified. It was a period when particle energies were so great, 10 to the 16 gigaelectron volts, that very massive particles, as well as quarks, leptons, and their antiparticles existed. Then, after 10 to the negative 35 seconds, the universe rapidly expanded and cooled, the warm epoch, 10 to the 29 to 10 to the 15 Kelvin, and the strong and electroweak forces parted company. As the universe continued to cool, the electroweak force split into the weak force and the electromagnetic force approximately 10 to the minus 10 seconds after the Big Bang. So this entire paragraph basically explains the first 10 to the minus 10 seconds after the Big Bang, which is right here, 10 to the, boom. 10 to the minus 10 is around here. So here all of the forces are unified. Over here we get the branching, which is gravitational force splits off from the strong and electroweak force. and then gravity continues on as its own. There's no more splitting happening. The universe expands rapidly, so the size of the universe grows like boom. The strong and electroweak forces split over here, so they are no longer the same. We got the strong force, and then we have the electroweak force, and then over here is the last splitting, the weak force and the electromagnetic force split, and we get the four fundamental forces, which are believed to be the same at the beginning of the Big Bang. This is an insane theory, guys. We could talk about this for hours, I'm telling you. But right now, I'm just going to finish the 7-minute summary. Observations of radiation and the primordial fireball. Robert W. Wilson and Arno A. Penzias with the Bell Telephone Laboratories horn reflector antenna. The first telephone, I think. I'm not sure. We got some other graphs, other evidence of an expanding universe, the Hubble law, Hubble constant. This Hubble constant. You can look at stars and how stars move and stuff, and you can figure out how old the universe is from this Hubble constant. So take a look at Hubble constant on YouTube or something like that. Recession of a quasar. You can kind of do some of these examples here. Will the universe expand forever? This is so interesting, man. And let's actually leave this for you guys to read if you're interested. I'm not going to read it here. Maybe it's a bit of a spoiler. Missing mass in the universe. Answer this problem here and you should be chilling, like your parents and friends are going to be super proud of you. It's a very difficult problem, so start early. Start at a young age. Mysterious energy in the universe, also an interesting problem you can put your energy into. Problems and perspectives. While particle physics has been exploring the realm of the very small, cosmologists have been exploring cosmic history back to the first microsecond of the Big Bang. Okay, interesting. We're going to zoom through. String theory, a new perspective. String theory has been clowned recently, but it is a super interesting theory, very, very much like high-level mathematics going on here, but I don't know too much about it. So here they kind of just talk about it at a surface level. I got some corruptions in my book here, so I don't really know what this graph is talking about. M theory, also very interesting, kind of really modern theory. 11-dimensional theory based on membranes rather than strings. And we got the summary here. I'm not going to go through the summary, but that is the final chapter. As you can see, like there are problems and a lot of things to learn for this chapter here, but it is very surface level kind of stuff. It's super modern physics, so you kind of just have to know like a couple of words here, a couple of key words. You can just kind of make some cue cards for yourself and test yourself in this way. I might do some problems on this, but I think my YouTube channel is going to be mostly on the relativity and quantum mechanics problems. And this stuff is a bit more like reading and kind of just understanding and remembering some stuff, kind of like a history exam. You got to read and remember a bunch of names, dates, stuff like that. The relativity and the quantum mechanics, there's a lot of problem solving and weird math going on there. So I think I'll focus on that. But let me know in the comments down below if you guys are interested in something specific. I can do it. But that finalizes the 7-minute summary. Thank you guys, as always, for watching. Peep out my other 7-minute summaries. Watch them all in order. And yeah, good luck with the studying. Peace out.